Alrighty, gang, welcome back. Good afternoon. Today, or close. Today is our last day. We're here. We're at the end. Beyond today, there's really not much more to do. We're going to talk about the specifics of what you will need to do. But most importantly, we're going to be learning how to solve the matrix equation AX equals B. So, we get some things set up here, and we can begin. If you tried to come to my office hours yesterday afternoon, I want to apologize. I had some pretty crazy shit going on at home, and I was only able to work with one student. Not the normal thing, but so this is MAC 1140, section number 009, which is of course pre-calc. Today is the 2nd of December 2021. And what we're doing today, we're going to discuss matrix inverses and solve the matrix equation AX equals B. This is all 10.5. Little announcement. I think I talked about this last time, but exam 4 is a take-home test. Posted to Canvas later today. The instructions are going to be there. They're going to be very clear. You need to print the thing. Then complete it. Then scan. And finally upload to the assignment in Canvas called exam 4. If you have a tablet or a touchscreen thingy that you want to do the test on instead, as long as you can write directly on the PDF, that's okay. What I don't want you to do is just write out the questions on notebook paper. So I want to preserve this formatting because these are things I want to be able to grade quickly and turn around for you as fast as possible. So yeah, for most of us, that's going to mean printing the thing, filling it out, scanning it, and uploading it. But if you have the iPad, whatever things that you want to use for that, to do it digitally, you're welcome to do that too. That's just fine, as long as you preserve the formatting. This is going to be posted today. And it will be due at the start of the final. Which for your class, again, I know we said this the other day, but I just want to make sure we're being super duper redundant about this, is December 7th at 1 p.m. So you have several days to do the thing. I would not recommend waiting until 12 p.m. on that day to do this. Please start on it like today, and as soon as you finish it and you've had time to look it over and you're comfortable and confident with your answers, go ahead and scan it and submit it. I will not take it after this time. Right? If you don't do it, if you don't get it submitted by 1 p.m. on the 7th, then I can't take it. Then it's going to be a 0, and you don't want that. So there's no reason for us to not do well on this. This is a test where instead of having 75 minutes, you have 5 days, and it is no longer, no harder than any regular test. You can use your notes and your textbook, but no other resources. And let me assure you, I have Mathway, PhotoMath, Symbolab, all that shit installed on my phone too. I run my own stuff through those as well. Please, 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 please don't use that stuff. I know what a genuine solution looks like. I know what a copied solution looks like. Don't use any other resources. Don't use those apps. Don't use a tutor. Don't copy somebody else's paper. I've caught people doing all of those things. I've had tutors come to me and say, so-and-so brought me a take-home test. Can I work on them with this? I've had people turn in papers that were obviously copied from each other, and I can't tell you how many people I have failed for handing in shit that was copied from Mathway and Symbolab. Really don't want to do that. You got 5 days to take a 75-minute test. Just sit down and take the time to do it, please. It's the least you can do here. Alrighty. You can use your notes on exam 4. Sorry. So I should, let me clarify this on the take-home test. The final exam is a regular proctored test, and you cannot use any outside resources on that. All right, another little note, the final exam must be taken online with me, not at the testing center. So throughout the semester, the testing center is happy to accommodate us as much as they can, but because the testing center is the designated place for fully online classes rather than this, which is a synchronous hybrid class, the testing center is the designated place for fully online classes to do their finals. They are busy. And the way the college works, you have to take the final at the designated time. So you have to start the final at 1 p.m. on the 7th. We're not allowed to move that around. The final exam schedule is very rigid and it's set before the start of the semester. The only way the testing center could even begin to accommodate us is if we opened up the window for the final to an all-day thing like we have been doing for the midterms, and that would violate several college rules. So the final exam, you got to take it online with me, and this means you need Zoom on your phone. And honor lock on your PC, laptop, whatever. If you don't have a laptop that can run honor lock, the college has the laptop loan program here. I'm pasting that in the chat. I know most of us have a phone and have a laptop, but still, if whatever, your webcam's broken, or it's an ancient laptop and you can't update Chrome, or something like that. If you know that your laptop cannot run honor lock, please go ahead and fill out this laptop loan application so we can take care of that. Similarly, if you don't have a phone that can run Zoom for whatever reason, I know it's 2021 and everybody can run Zoom on their phone, but if for whatever reason you can't, reach out to me. I'll figure something out for you. So that's it. The final, we have to do the final in the kind of standard way for this class. Can't do it at the testing center. Any questions for me on exam 4 and the final? Okay. I'll say one other thing about the final. You really want reliable internet access. So if you know that the Wi-Fi at your house drops like every 10 minutes or something like that, you certainly want a backup. You want to make sure that you've got a place where you can take the test, that your internet access will be consistent. And then, of course, you need the working phone and the laptop capable of running honor lock. Other things you will need, if you haven't been using honor lock this semester, if you've been doing everything at the testing center, just as a heads up, you will need your Santa Fe ID or driver's license to verify your identity on honor lock. That's it, right? Okay. So let's get into today's stuff. All right, recall. that a linear system, like, we'll just do a little 2 by 2 here, say negative 3x minus 5y equals 4, and 2x plus 3y equals 0 can be written, this was the big payoff last time, can be written as a matrix equation AX equals B, where A is the standard coefficient matrix, just the coefficients over here, negative 3, negative 5, 2, 3. X is the column matrix made up just of the variables little x, little y. And B is the column matrix of right-hand sides, 4, 0. We saw last time that if you write out this matrix equation, this matrix times this matrix equals this matrix, and you go ahead and do the multiplication, A times X, you get a 2 by 1 whose first entry is this, and whose second entry is this. So in order for those to be equal, you would need negative 3x minus 5y to be 4 and 2x plus 3y to be 0. In other words, this equation really is equivalent to the original system. And you can do this for a larger system, like a 3 by 3 or a 4 by 4 in the same fashion. You just take the coefficient matrix, the column of variables, and the column of right-hand sides. We want to solve this matrix equation. Kind of in the same way we solved the matrix equation from our last lecture, working just with that. Working in the matrix notation. And that would require doing something like dividing both sides by A, right? If I want to get X alone, right now X is being multiplied by A, so I'd want to divide by the matrix A, whatever that might mean. So I'm putting it in these quotes because we have not defined division for matrices. There, in fact, is no division operation for matrices. It just doesn't exist. But we have defined multiplication for matrices. It turns out, those interested, it turns out that the set of all matrices of a given size, like the set of all 2 by 2 matrices, form a structure called a ring, where you can add two things, you can subtract them, you can multiply them, but there isn't necessarily a well-defined division operation. So the best we can do is try to describe division in terms of multiplication. And thankfully, those two are intimately related. So that's where we're going to go. I'm going to kind of try to talk about how to get rid of that matrix A from the left-hand side here by multiplying both sides by some other matrix. And in order to get you there, conceptually, I want to talk about division in terms of real numbers and how that can be rephrased in terms of multiplication. But this is where we left off last time. This is kind of the picture we had at the end of the last lecture. Linear system turns into matrix equation. Solve the matrix equation by getting rid of this matrix A, which would just give me X equals some stuff. And then X is are my variables. So once I have solved this for the matrix X, I've got my solution to the system. I should put the little bars on this to make it a clear capital X. All right, how do we do this? Let's talk about division as an operation. Division is a nasty operation. It's not commutative, it's not associative. And you can't even do it all the time, right? Like you can't divide by 0. But when you can do division, it can always be rephrased in terms of multiplication. So I'll say, give him a real number, not a matrix, just a number, call it lowercase a, dividing by a is the same as multiplying by 1 over a, which we can rewrite in the powers as a to the negative first. Right? So like dividing by 2 is the same as multiplying by 1/2. Dividing by 7 is the same as multiplying by 1/7. So this lets us rephrase the operation of division in terms of multiplication by something. In order to kind of get us closer and closer to talking about doing this for matrices, I want to try and describe what this thing is, right? I mean, sure, 1/2, I know what 1/2 is, it's 0.5, it's, you know, there's a bunch of, it's a measurable quantity, but we need to sort of abstract this concept to a place where we can describe a similar thing for matrices. So a question, what is a to the negative first? Now, if a is a real number, a to the negative first, or 1 over a, what is that thing? What is 1/2? One way to describe this, a to the negative first is the real number which, when multiplied by a, gives the number 1. That is, we can characterize this number, a to the negative 1, by saying a to the negative 1 times a is equal to 1. And if you want, and a times a to the negative 1 should also be equal to 1. So here we have the necessary pieces to start trying to talk about what it might mean to divide by a matrix. A division is the same as multiplication by this inverse thing. This is called the multiplicative inverse. So dividing by a is the same as multiplying by a inverse, so the reciprocal of a. And the reciprocal of a number is this new number that you get, such that when you multiply it by the original, you get 1. In order to generalize this to matrices, we need the matrix version of the number 1. So my question to you, and I really want an answer here, any thoughts are welcome. What is the number 1? No. Strange question, but yeah, what is special about the number 1? what properties does the number 1 have that I would want the matrix version of the number 1 to also have? Does anybody want to share their thoughts or take a guess at what we're getting at here?
Well, anything to the 0 power, like the 0 exponent equals 1.
Very good. Anything to the 0 is 1, right? If I multiply a to the -1 times a to the 1, that's the same as a to the 0. So 1 is the number that you get out when you raise anything to the 0 power. That's a really good observation. Can anybody tell me anything else kind of like that? Think even more like elementary school. Think even simpler.
Everything which is multiplied by 1 is the same number.
Hell yes, that's the main thing we're after here. So remember, we're specifically talking about multiplication. So what's special about the number 1 when we're talking about multiplication? For any number a times 1 is equal to a. In fact, for this reason, we call this thing, we call 1 the multiplicative identity. Think about what the word identity means. It's who you are, it's oneself. As a function, the identity function is a function that leaves everything alone. Like f of x equals x is the identity function because it outputs the same thing it input. Just for fun here, the abstract algebraic terminology for this reciprocal a to the -1 is called the multiplicative inverse. So the multiplicative inverse is the thing you multiply the original thing by in order to get 1, which is the multiplicative identity, because if you multiply anything by 1, you get that thing back. This is the property that I really want my matrix 1 to have. Such a matrix does exist. In fact, it's not just one matrix, but it's many matrices. Because remember, let me be explicit about this. I want A times my matrix 1 to be equal to A. I'm going to call that matrix 1I. And I want to be able to do it in the other way also. A times I is also equal to A. So my matrix version of 1, I call it I, and I want it to have this property that if you multiply any matrix by I, you get that matrix back. Such a thing will be the critical element to defining the inverse or reciprocal of a matrix. Okay. Rather than making you guess or trying to discover the thing, I'm going to just tell you what it is. So remember, in order to do this multiplication, I has to be a certain size, right? I need here the columns of I to be the same length as the rows of A. And here I would need it the other way around. I would need the rows of I to be the same length as the columns. The columns of I to be the same. I wrote this the same way, didn't I, both times? Damn. Sorry. And I times A to be equal to A. Yeah, so here I would need the columns of I to be the same length as the rows of A. And here I need the rows of I to be the same length as the columns of A. So for any integer n, here it comes. For any integer n greater than 1, we can define such a matrix. And I'll just show you what they are and then verify that they have this property we want. If we're talking about a 2 by 2, I want these to be square matrices so I can multiply on either side. If I'm talking about a 2 by 2, then this is the matrix 1, 0, 0, 1. If I'm talking about a 3 by 3, then this is the matrix 1, 0, 0, 0, 1, 0, 0, 0, 1. And if I were talking about a 4 by 4, I would call this the matrix I, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, and 0, 0, 0, 1. Now, because the specific matrix depends on the size that you're talking about, we usually index them with a little number here, I2, I3, I4. And in general, IN is the n by n matrix with ones along the main diagonal and zeros everywhere else. These are called identity matrices. And when the size is implied by the context, like if the matrices we're working with on a particular problem are all 2 by 2s, then rather writing I2, I just write I. There is an I1. I1 is a 1 by 1 matrix, which is just a number. I1 is the number 1. So this is the matrix that generalizes that property of the number 1 that I care about so much. That when you multiply any matrix by I, you get the matrix back that you started with. I'd like to verify that for you. And I'm just going to show you in a simple.
Can you go back for 1 second?
Sure, sure.
Oh, thank you.
Yeah, no problem. It's a lot to write here. So just kind of thinking along for a minute, I will verify that these matrices do the things we want them to do. The inverse of a matrix then would be a new matrix such that when you multiply it by the original matrix, you get I, right? Just like 2 times 1/2 is equal to 1. Therefore, 1/2 is the multiplicative inverse of 2. A times A inverse should be equal to I if A is the multiplicative inverse of, or A inverse is the multiplicative inverse of the matrix A. All right, gonna move on. Really quick, I just want to verify that AI is equal to IA is equal to A for the 2 by 2 matrix, 3, -1, 4, 2. So I'm just going to try and convince you that the matrix I2 does what it's supposed to do. So let's compute A times I first. This would be 3, -1, And that's supposed to be a 4. It looks like a 9, doesn't it? 4, 2 times 1, 0, 0, 1. And the reason we're going to check both of these separately is because you know that AB is not always the same as BA, right? We saw that in our last lecture. Matrix multiplication is not commutative. The order does matter. But hopefully for the identity matrix, it doesn't. So remember how you do this product. You're going to take the first row here and the first column here, and that will give you the 1, 1 entry in the result. These are both 2 by 2s, so we're expecting to get a 2 by 2 out. 3 times 1 minus 1 times 0. That is the first entry. Row 1 of A with column 1 of B. Now to figure out what goes here, I take row 1 of A with column 2 of B. That's 3 times 0 minus 1 times 1. To figure out the 2, 1 position, I take row 2 of A and column 1 of B. So that's 4 times 1 plus 2 times 0. And the 2, 2 position, I take row 2 and column 2. That's 4 times 0 plus 2 times 1. And simplifying, 3 minus 0 is 3. 0 minus 1 is minus 1. 4 plus 0 is 4. And 0 plus 2 is 2. And that is A. Hooray, that's good news. Let's try in the other direction. If I multiply I times A, if I put the identity matrix first, does that still work? I hope so. But in mathematics, we're inherently very skeptical. So rows here with columns here now. So I'm taking rows from I and columns from A. So that's 1 times 3 plus 0 times 4. Row 1, column 2 gives me 1 times negative 1 plus 0 times 2. Row 2, column 1 gives me 0 times 3 plus 1 times 4. And row 2, column 2 gives me 0 times negative 1 plus 1 times 2. And if I simplify this, 3 plus 0 is 3. Negative 1 plus 0 is negative 1. 0 plus 4 is 4. And 0 plus 2 is 2. And is this A? Negative 142, it's negative 142. Hell yeah. So this works fine. And hopefully you can see that if this was any other 2 by 2, it would work the exact same way. A 3 by 3, I can do it. It'll take a little bit of time. Let's just do it. Maybe I'll do just one direction. Let's verify that IA is equal to A for the 3 by 3. 1, 3, negative 1, 1, 4, 0, negative 1, negative 3, 2. It's really just more practice with matrix multiplication here. So I times A. Now we're talking about the 3 by 3 identity. That's 1, 0, 0, 0, 1, 0, 0, 0, 1 times A, which is 1, 3, negative 1, 1, 4, 0, negative 1, negative 3, 2. I'm multiplying 2 3 by 3, so the result should be another 3 by 3. And my 1, 1 position, is going to come from row 1 here, column 1 here. So it's 1 times 1 plus 0 times 1 plus 0 times negative 1. My 1, 2 position, row 1, column 2, that's 1 times 3 plus 0 times 4 plus 0 times negative 3. One, 3 position, again, row 1, now column 3, 1 times negative 1 plus 0 times 0 plus 0 times 2. Oops, 0 times 0 plus 0 times 2. And then we do the same thing now, row 2, column 1, that's 0 times 1 plus 1 times 1 plus 0 times negative 1. Row 2, column 2 is 0 times 3 plus 1 times 4 plus 0 times negative 3. 0 times 3 plus 1 times 4 plus 0 times negative 3. And then the 2, 3 position, I take row 2, column 3, that's 0 times negative 1 plus 1 times 0 plus 0 times negative 2. So 1 times 0 here, and then 0 times 2. And then the third row, we use the third row first column. That's 0 times 1 plus 0 times 1 plus 1 times negative 1. For the 3, 2 position, I use the third row second column. That's 0 times 3 plus 0 times 4 plus 1 times negative 3. And for the 3, 3 position, I use third row third column. That's 0 times negative 1 plus 0 times 0 plus 1 times 2. So here's the resulting 3 by 3 matrix. And if I simplify, I should get the original matrix A. Let's see. 1 plus 0 plus 0 is 1. 3 plus 0 plus 0 is 3. Negative 1 plus 0 plus 0 is negative 1. Row 1 looks good. 0 plus 1 plus 0 is 1. 0 plus 4 plus 0 is 4. 0 plus 0 plus 0 is 0. Row 3, 0 plus 0 plus negative 1 is negative 1. 0 plus 0 plus negative 3 is negative 3. 0 plus 0 plus 2 is 2. Okay, did it work? Yeah. This is A. Right. This takes a little while. I don't want to waste the time to do the other direction, but it would work there also. So these matrices IN, or if you just want to refer to all of them as I, that's fine. They have that same important property that the number 1 has. When you multiply it by any matrix, you get that same matrix back. So then, what's the inverse of a matrix? We can now define in order to do this, the matrix A has to be square. As the new matrix, call it A inverse, satisfying these kind of two different equations. A inverse times A should be 1, or I, and A times A inverse should also be I. In that same way that 1/2 times 1/2 times 2 is 1, and 2 times 1/2 is 1. This is your definition. So if I give you two matrices and ask, are these inverses? The way you figure that out is by checking both of these products. So let me check. I'm going to propose a certain inverse, or maybe I'll find and check. Yeah, let me tell you. So we've defined what the inverse of a matrix is, but the question is now, how does one find a inverse given the matrix A? And the answer here is you write down your original matrix augmented by the identity. Remember what the augment means. You just take your matrix and kind of glue this other thing onto it. And you perform row operations until you have the identity on the left. And once you've done that, the thing that will show up through that procedure is the inverse on the right. So you start with this, and you do row operations until you've got this into that reduced row echelon form, where it's just ones on the diagonal and 0 everywhere else. As you do those row ops, this thing will change. And after you've completed all the row ops to get the identity over here, the thing that will show up on the right will be the inverse of your original matrix. So I'm going to do this for you now. And then we're going to check that they are inverses. Let's do it with the matrix we worked with earlier. Let's find and verify the inverse of the matrix A from our little 2 by 2, -3, -5, 2, 3. So first I'm going to augment my matrix A by the identity matrix. That's -3, -5, 1, 0, 2, 3, 0, 1. And then I'm going to run row ops on this until the left-hand side there is the identity. So what do I want to do? I want to make this a 1. I want to make this a 0. I want to make this a 1 and this a 0. First, let me make this a 1. So I'm going to make R1 -1/3 my old row 1. I'm going to divide through row 1 by -3. That will give me 1, 5/3, and then -1/3 and 0 here. Row 2 doesn't change. Now I want to kill the 2. To do that, my new row 2 will be my old row 2 minus 2 copies of my old row 1. So I'm going to subtract 2 times row 1 from row 2. This time row 1 doesn't change. 1, 5/3, -1/3, 0. I do have some fraction arithmetic to do. -2 times this plus this is 0. That's by design. -2 times 5/3 is -10/3. I'm going to step to the side to do the arithmetic. So I need to add negative 10 thirds to 3, which is negative 10 thirds plus 9 thirds, which is negative 1/3. So this will be a negative 1/3. I need to multiply this by negative 2. That's positive 2/3. 2/3 plus 0 is just 2/3. No need to do work there. And negative 2 times 0 is 0 plus 1 is still 1. So as we slowly make the identity show up on the left, the inverse is slowly showing up on the right. I've got column 1 happy, he's 1, 0. I need column 2 to be 0, 1. So I need to make this a 0, and I need to make this a 1. I'm going to make this a 0 first, because these are both fractions with denominator 3, so it's kind of easier to work with them like that. If I multiply row 2 by 5 and add it to row 1, so row 1 is old row 1 plus 5 times old row 2. 5 times 0 plus 1 is still 1. Let me write down row 2 first. 0, negative 1/3, 2/3, 1. All right. 5 times this plus this is still 1. 5 times this is negative 5/3 plus this is now 0. 5 times 2/3 is 10/3. 10/3 minus 1/3 is 9/3. Maybe I'll write this one out too. That's 9/3, which is just 3. So this piece will become a 3. And what am I doing? Multiplying by 5 and adding up. So 5 times this plus this is just 5 plus 0 is 5. And now I've got 1, 0, 0, negative 1/3. So I need this to be a positive 1, which means I'm going to multiply through row 2 by negative 3. So my new row 2 is going to be negative 3 times my old row 2. Row 1 doesn't change. 1, 0, 3, 5. This is going to be 0, 1. And then negative 3 times 2/3 is negative 2. Negative 3 times 1 is negative 3. Now this is my identity. So this must be A inverse. In other words, from here it looks like A inverse is the matrix 3, 5, negative 2, negative 3. That's my claim.
But didn't we just like change the signs of what we had in the first one? Like what we had A first?
So there's a few things that happened here. The 5 and the 2 swapped. And also we've got some sign changes. Yeah. Or sorry, the 5 and the 2 didn't swap. These guys changed sign. Right. And I'll explain to you. There's a little shortcut for coming up with this. It only works for 2x2s, and this only came out so nice because the determinant of this matrix is 1. Determinants you'll see later, not a part of this class, but yes, there is a nice relationship between the original and the inverse. It's not always this nice though. Yeah, it does seem to be the case that even more nice here is that A inverse is the same as negative A. That's definitely not always true. But we want to verify it. So we want to see that A times A inverse is equal to I. So that's negative 3, negative 5, 2, 3 times 3, 5, negative 2, negative 3. And if I do multiply these matrices, rows here with columns here, negative 3 times positive 3 is negative 9 plus, oh, hang on, did I make a mistake? let me double check something. Those should negate. And these should swap. Did I make a mistake in my row operation somewhere? Oh, I think I might have. Yeah, this shouldn't be this nice. Hang on one sec. So did I write him down correctly? Yes. And then dividing by -1/3. Divided by -3. And then multiply by 0, 2. -2 times this plus this is 0. -2 times this is -10/3 plus 3. And then it's -1/3. -2 times this is -2/3 plus 0 is. Oh, wait, no. Yeah, negative. Okay. Well, that's good. Okay. Yeah. Yeah, it looks like I made a little mistake somewhere. We're going to add 5 times this to this, right? So this doesn't change. 5 times this plus this, -5/3. 5 times this is 10/3 minus 1/3 is 9/3. 3. 5 times this is 5 plus 0 is 5. Okay. And then multiply through by -3. I think the inverse here, let's see. These should swap. And those should negate. -5/2. Oh no, maybe this is right. Okay, sorry, maybe I'm being anxious here. So -3 times +3. Oh yeah, we're fine, we're fine. This is -9 plus -5 times 2. Yeah. Okay, let me write it out. We're fine. -3 times 3 plus this times this plus this times this. -5 times -2, which is 10. Yeah, we're fine. -3 times 5 is -15. -15 plus +15. Down here, we have 10 minus 9. And here we have 10. Sorry, that's the 2-2 position. Oh, damn, my brain is fried. 6 minus 6. Yeah. And then this one is 10 minus 9. Okay. So what do we get here? This is -9 plus 10 is 1. -15 plus 15 is 0. 6 minus 6 is 0. And 10 minus 9 is 1. This is good. So this is I2. And if we multiply in the other way, A inverse times A. Expect a 2 by 2, and we take row 1, column 1, so that's 3 times -3 plus 5 times 2, that's -9 plus 10. Row 1, column 2 is 3 times -5 plus 5 times 3 is -15 plus 15. Row 2, column 1 is 6 minus 6. And row 2, column 2 is +10 plus -9. And yeah, again, we do get 1, 0, 0, 1, which is the identity. So we're in good shape. We found the inverse and it is correct. Just had a little panic there, but nothing wrong. We did everything right. Okay, why is this useful? Why do I care about matrix inverses? Well, remember, we wanted to solve the equation AX equals B. So to finish things up here, we are going to now solve that linear system we started with. going to solve the linear system. Negative 3x minus 5y equals 4, and 2x plus 3y equals 0 by solving ax equals b. Come here. So remember, our system is equivalent to ax equals b, where A is this matrix, -3, -5, 2, 3. Capital X is the matrix little x, little y, and the matrix B is 4, 0. Now, AX equals B. Here's the big payoff, right? We can do this all at once. This is the same as A inverse times A times X equals A inverse times B. I can multiply on both sides by A inverse. What is A inverse times A?
One.
Yeah, or the identity, right? Like the matrix version of 1. So this is I times X equals A inverse times B. What is I times X? What is this left-hand side? If I multiply the matrix X by the identity, I should get
I.
well, I'm multiplying X by I. So I times anything is just that thing, right? So if I multiply the matrix X by the matrix I should get the matrix X back. And that's good because that's what I wanted. All right, we're trying to solve this matrix equation for X. And we know that A inverse is the inverse matrix we just calculated, right? Which was 3, 5, -2, -3. Yeah. So A inverse times X is 3, 5, sorry, 3, 5, -2, -3. A inverse times B, here's A inverse, and B is just this column of right-hand sides, 4, 0. And this is the matrix X that I'm trying to find. This is the matrix that just has my solutions in it. So that's 3 times 4 plus 5 times 0. That's 12 plus 0. And -2 times 4 minus 3 times 0. That's -8 plus 0. So this is just 12, -8. And that means that's the solution to your system. Little x is 12 and little y is -8. So this is the magic. It's like a single step thing. If you have the inverse matrix, then to solve AX equals B, you just have A inverse times B. X is A inverse times B. And then the only computation you need to do is multiplying these matrices. It's incredibly fast. So we can solve linear systems very quickly if we have the inverse of the coefficient matrix A. That's kind of the big take home, right? We've seen many different ways to solve linear systems. You can use substitution in some cases. You can use elimination in all cases. You can rewrite the system as an augmented matrix and use row operations to get that into triangular form and then back substitute. Or, and this is kind of the biggest brain way to do it, you can write the matrix equation AX equals B, where A is just your coefficient matrix, not augmented. Find the inverse to the matrix A, and then solve that matrix equation for the matrix of your solutions, X. The catch is, in mathematics, there's no free lunch. Finding the inverse of A is exactly as much work as regular elimination. In fact, if you look at the procedure, it's literally the same work, right? You're row reducing the matrix A into that reduced row echelon form, which is the same procedure that you use to solve the system as an augmented matrix. And although we didn't think of it that way back when we were row reducing the systems rather than writing them as matrices, it's the same work we were doing there. So finding the inverse to a matrix is not fast. If you have the inverse to the matrix, then solving the system is very fast. And I want to make one point very, very clear here. When you solve the original system by using elimination, right? Like eliminating one variable and then back substituting and all that, or when you solve the system by writing it as an augmented matrix and row reducing that, implicit in there throughout the whole process is this right-hand side. What this procedure does is it divorces the solution process from these numbers 4 and 0. I didn't need these numbers to come up with this inverse. So if I gave you this system like 5 times, but with different numbers on the right here, you could solve all of those at once by finding the inverse. Whereas if you used one of the other methods, you would have to go back through and resolve each time. So really the sense in which this new method is better is that it solves every system where these are on the left all at once. I could change this to 0, 0 or 0, 4 or negative 1210 or pi e. And then all you'd have to do is change these and recalculate this product. The inverse matrix doesn't change. And the way linear algebra kind of develops from here, this whole field of mathematics, is by asking ourselves, what things can we put over here so that there will be a solution? And if the coefficient matrix has an inverse, then there will be a solution for anything you put over here. And this is where people start learning about the concept of dimensionality, which is a geometric thing. You start studying these spaces of what are called vectors. And it's very, very cool stuff. It's very beautiful, but it is beyond the scope of this course. So this is actually about where we stop in this class. We stop right here with this ability to invert matrices and this understanding that you can rewrite a system of equations as a matrix equation. I would like to solve one more system like this for you, but we don't have time to cook up the inverse in the way we did. So I'm going to show you one thing real quick before we go, and then I'll solve one more system if we have time. there is a trick for finding A inverse when A is a 2 by 2. So if A is the 2 by 2 matrix A, B, C, D, and AD minus CB is not equal to 0, then A inverse exists, and A inverse will be equal to 1 over AD minus CB times the new matrix you get by swapping A and D and negating C and B. So that would be D, negative B, negative C, and A. You can compare this to what we had in the last guy, and you'll see that it works. This number right here, AD minus CB, that's called the determinant. So not every matrix has an inverse. Even square matrices, there are plenty of 2 by 2 matrices that don't have inverses. Those correspond to systems that don't have solutions or have infinitely many solutions. But if your 2 by 2 matrix does have an inverse, it will be in this form. And you can use this as a speedy way to calculate the inverse. All right, one more system. We're going to solve the system. Let me see. X plus 3y minus z equals 2. X plus 4y equals 7. And negative x minus 3y plus 2z equals negative 1. Using the fact that the matrix A, which here would be 1, 3, negative 1, 1, 4, 0, negative 1, negative 3, 2, has inverse what is this one? I calculated this ahead of time. This is 8, negative 3, 4, negative 2, 1, negative 1, 1, 0, 1. So what we do is, again, we just write x equals the column x, y, z, and b equals the column 2, 7, negative 1. So our system is equivalent to AX equals B. Which we have seen is equivalent to X equals A inverse B. And A inverse times B is this matrix times this matrix. That's 8, negative 3, 4, negative 2, 1, negative 1, 1, 0, 1. Times my vector or column, sorry, of right-hand sides, 2, 7, negative 1. And doing this computation, I have 8 times 2, 16, minus 3 times 7, that's minus 21, minus 1 times 4, minus 4. That's the first solution. I'll clean it up in a minute. Negative 2 times 2 is negative 4. 1 times 7, 7. Negative 1 times negative 1 is plus 1. And then my last guy is 2 times 1, which is 2, plus 0 times 7, which is 0, plus 1 times negative 1, minus 1. So what is this? 16 minus 21 is negative 5, minus 4 is negative 9. Negative 4 plus 7 is 3 plus 1 is 4. And 2 minus 1 is 1. So the solution is, you could write it as x equals negative 9, y equals 4, z equals 1, or you could write the ordered triple, negative 9, 4, 1. So that's the magic here. If you have your inverse, then solving a system is incredibly fast. And you can not only solve this system fast, but if you change the 2, 7, or negative 1 to something else, I could solve all of those systems at the same time incredibly fast, just by multiplying A inverse times B. That's sort of the beauty of this field of linear algebra that we're studying. But let me tell you that matrices are fantastic and amazing objects for a million other reasons. One of my first kind of big projects in graduate school was computing a determinant for a very large matrix made up of entries from these number theoretic functions that measure common divisors between two integers. Matrices show up in the study of graph theory, which is like computer networks, where you picture like one computer with lines going to all the other computers it's connected to. There are these things called adjacency matrices, which tell you, one computer is connected to another computer, you put a 1 in this spot. And then by studying the algebra of those matrices, you can make conclusions about the network. There are so many different places that linear algebra, the study of matrices, becomes important. And I hope that you've gotten just a little taste of kind of how fascinating these objects are. That is it for us and for pre-calculus, lads and ladies. This is the last bit of material that will be on your take-home test. There's one other tiny bit of material that will be on your final, and that is the stuff I talked about the other day, the sequences in series, which I'm going to kind of record a little lecture for you on. I'll be very gentle on that stuff on the final. I just do want to make sure I've shown you the notation. Before I let you go, there are some things I would have liked to talk about this semester. One of them is that sequences and series stuff, and we're going to do that. Other topics you should look into to prepare yourself for calculus. See, what I've found over the last few years teaching this course online is that a lot of us get here without the comfort and familiarity with function notation and polynomials that we need. So we stretch that section out a little bit, and that means we squeeze these others. So sigma summation notation. This is going to come with a video lecture, and it will be on the final. Nothing hard, I promise. Very simple. As long as you take the time to understand the notation, work the example problems I give you, you will be just fine on this. But I need you to know what this symbol means moving into calculus, because you're going to see this a little bit in Calc 1 and a lot of it in Calc 2. Partial fractions. I got in trouble because I used to teach this in pre-calc here at Santa Fe, and I was told I need to stop doing it. I don't know why. It was a part of pre-calculus back when I took pre-calculus, and it's very useful. We use it a lot in Calc 2, And if you take Calc 2 here at Santa Fe, your professor will assume you've never seen it before, and he or she will teach it to you from scratch. But if you take Calc 2 at another place, a university or something like that, they might assume that you've seen this before. So it's something worth looking up because we use it a lot in Calc 2. The last thing is conic sections. And these are like circles, hyperbolas, parabolas, which we did talk about, and ellipses. These are very cool objects from geometry. And while we did discuss parabolas this semester, there's a lot more we could have said about them that we didn't. These do not show up in calculus so much. I mean, they will arrive from time to time as examples, but it's not the case that you having a lack of knowledge about the geometric definition of an ellipse is going to hurt you. But you should know the equation of a circle. And I'll just tell you what that is. That's x minus h squared plus y minus k all squared is equal to r squared. This is something that you definitely will need in various places in calculus. This is a circle centered at the point h comma k, whose radius is r. Really, the only thing from conic sections that you're going to need in calculus is this. But the geometry here is quite cool. And in Calc 3, when you talk about kind of higher dimensional functions whose graphs are surfaces or solids in 3D space, thinking about the geometry of these things will be relevant. So this is stuff that either doesn't make it into the course because Santa Fe, or didn't fit into the course because of our timeline. And that's not the end of the world. Trust me, you will be benefiting from the time we spent on polynomials and whatnot earlier. But this is stuff I would like to talk about if we had a little more time. The one that I consider absolutely essential is the sequence and series stuff. So I will be posting a video lecture for this, and I will be testing for it on the final. So please make sure you watch that video lecture. And I will give you some example problems to work in that lecture. If you work those, I promise you, you'll be fine on the final. Partial fractions, no longer taught at Santa Fe in the pre-calculus class, but other institutions, if you transfer, will assume that you learned this. So I strongly recommend after the final, when you've got space in your brain, go ahead and watch a video or two on partial fractions. It's very, very cool. It's a way of splitting big fractions up into littler fractions. And then conic sections. Conic sections, they're just beautiful. There's not always time to dig deep on them in pre-calc, and that's okay. But these are quite beautiful things that, you know, kind of started the study of analytic geometry. So if you have a bent for geometry, I strongly recommend spending some time playing around with conics. They're very cool. But that's it from me, guys. That's it. That is the end of pre-calculus and even the things that I wish we could do that we're not doing. If you need anything from me, you know the rules, right? Canvas, Discord, email, office hours are the normal way to get a hold of me. Remember, your final exam is on the 7th. And before the final exam, I need you to complete the take-home test, exam 4. I'll be posting that to Canvas right now. You need to either print it or complete it digitally because we want to preserve that formatting. If you haven't done the Jello, please do the Jello, that worksheet on transformations. That way I can give you some extra credit points on test 2. And that's it from me. All righty. Like I said, if you need anything, please reach out. Remember, the final has to be taken online, so you got to make sure that you have the technology necessary to do that. I hope you guys take good care of yourselves between now and the final, and if you need help with anything, don't hesitate to ask. Bye.